So thank you very much for having invited me to present here some work about crowd simulation and the prediction of crowd motion. Let me start immediately with a disclaimer that I do not consider myself as an expert in motion prediction, as it is meant here in this community. I'm coming from the robotics path planning community, and I moved rapidly to the topic of autonomous characters and computer animation to finally end with some work on crowd simulation that I'm interested in for 15 years now. But we came to the problem of HTP or trajectory prediction to actually address some problem that we worked on robot crowd navigation during the crowd project, if you know it. And our plan was initially to start with the idea of using our best crowd simulation techniques and to embed it on board the robot, that the robot could use to actually try to understand and predict what was going around him. And I have to say that yeah, our interest in recent definitions of HTP problems came with the PhD of Javad Amérian. And he was really interested in, for example, the work of Alexandre Alahi, who is in the room. And he really convinced me that data-driven techniques would be more relevant to be used here than crowd simulation that is mainly knowledge-driven, as I will explain. So this presentation aims at discussing some relations I see between the field of crowd simulation and the one of HTP in robotics, and hopefully to give the audience some new perspective on this problem. I think I totally failed in giving this presentation the best possible structure. I hope it will be clear anyway, but please ask questions in the end to clarify things. So crowd simulation, to start, what is that? Crowd simulation objective is to compute the motion, so to design some softwares to compute the motion of a virtual crowd that replicates more or less the one of real crowds. So has to study, for example, understand crowd behavior or predict them. And the world of crowd simulation is split in two, with two approaches and two scales at which we observe the crowd motion phenomenon that we are used to call microscopic or macroscopic ones. To simplify, this is on the left video. I hope you can see it and it's smooth enough. What would be a microscopic perspective where you study the crowd motion by detailing what is happening at the individual level, how each of these person is actually forming motion trajectories based on the interaction he has with the environment or with people around him. And on the right, we illustrate what would be more a macroscopic perspective, where you do not try to distinguish anymore individuals, but you consider the crowd as a whole that is moving. So this leads to different kind of modeling approaches. One would be typically what you could call an agent-based approach, where you try to explain the trajectory of each individual from its motivations, for example, or all the interactions one can have with neighbors. The other perspective would be more to model the crowd like a field of changing density that would vary in space and time, and you try to compute this based on physical laws, such as, for example, that there is no loss in matter and there is sort of a continuum here. So I will focus, and my work is focused on the microscopic approach, the one on the left, and I will talk only about microscopic crowd simulation from now. And you have to understand that crowd simulation, so how to reach really the motion of a whole crowd, will not be simple and will be based on several components that will address different levels of this human behavior. So typically at the highest level, you will talk about behavioral modeling. So what people are here for, what do they gather here, and what they plan to do, right? So you can deal, for example, with symbolic task planning here, where then they have to start moving in the environment. So there is a form of spatial reasoning, or typically a path planning problem that is set. And then since the environment is very dynamic, there will be a need to adjust this plan according to what is happening at the local level. So typically collision avoidance, grouping, or these kind of things. And then eventually, because all this is modeled in 2D, you want to go for a 3D animation visualization of the results. I will go back to this later on. So that's interesting here because there are several words here that can take us back to this problem of trajectory prediction. So to start with, there is this common goal of predicting a motion, here the one of a crowd, but in the hand, as you can see, it ends up with predicting each motion of each individual composing this crowd. And also, I think just like trajectory prediction problems, you cannot take this problem as a whole. You need to split it into different levels. So you will not predict, like for example, what would be your locomotion trajectory in a whole environment, the same way you will predict what is the adjustment of a local motion due to, for example, collision avoidance. And interestingly, also there is these errors I've not described, but generally the crowd simulation problem is addressed this way. So you start from the general purpose of each agent, and then you go down the scale to really compute the motion. But actually what is happening locally could also have an impact of what you do. For example, if you try to follow a path that you have planned, and then at some point you end up into a crowded area, fully busy and jammed, then you may reconsider this choice. So there is a feedback here that we can call scale coupling that will make communicate each component not only from up to down but also down to up. So yeah, I think that data-driven modeling is also able to deal with this question, whereas knowledge-based approach is not that good at doing this. Anyway, so let's explore a bit what is the usual way by which we simulate crowd, and where I call this HTP, the modern modeling approach that are used in HTP could help here. And typically, I'm taking this example of a 1D flow of people, so where all people are doing the same thing, which is moving in one direction, and forced somehow to follow one another, not to enter in collision. And interestingly, in this simulation of this flow, you can see that there is this phenomenon where some people are stopped here in blue. The color will show the motion velocity, and this zone where people are blocked here is moving backwards. So actually, this is something that in simulation you may want to get, because simply some experimental observation of this phenomenon will reveal this, that indeed, when you ask a number of people, so these are some laboratory experiments we have performed in 2010, asking some people to follow one another, not being allowed to overpass, for example, and we recorded their trajectory, and we saw that at given densities, you have this phenomenon that is illustrated here. So these are individual trajectory along this circle in time. And what you see here is that each individual is experimenting this sequence of moving forward and being stopped and move forward again. So if you follow one trajectory like this is what you will see. And if you look across the whole line of people here, what you see is that the position where people are stopped is moving backward. And on this replay of experimental trajectories, this is very clearly visible. Okay, so what lesson we can have here? First of all, is that what's interesting in crowd simulation, and this is something where that HTP could take a look at, is in this simulation on the left, what we do here is we just embed a model of following behavior in those agents, and all the definition of this model that is uncrafted, to be clear, and the parameters which are learned from experimental data say that you should match the speed of your predecessor, and eventually keep some distance with him, and you manage these two aspects. From this, one can explain the formation of these stop-and-go waves. Okay, so this is something we are successful at getting in simulation. But what's interesting is that there is no tuning of this model that will match all the possible densities and all the possible configuration of this 1D flow. Which means that, and especially what is happening is that you get some instability in the simulation if you don't tune the parameters according to each density level you want to model. And this is, to me, something that data-driven modeling and prediction of what is your motion in this given situation could address more carefully, because the model would probably generalize better across different situations. And my questions to the field would be this one, like, how are we able to predict correctly the speed propagation, the formation first, and the speed propagation of those waves, stop-and-go waves, based on data-driven approach? This would be really interesting to figure out, and especially because it's not clear here. For example, if we have a single behavior of following, I was explaining that if you consider a single behavior here, it's not certain you will have a successful simulation of it. Or maybe we have an alternance of two behavior here, like you are following people when they are making some distance with you, for example, and start avoiding collision when you see them stopped in front and you need to decelerate. Or something in between. That could be the same behavior, but where its parameters, let's say, are readjusted according to the situation. So yeah, so typically the questions we are asking ourselves during the process of crowd simulation, and I think again that we should get out of this knowledge-driven approach to go more towards machine learning and data-driven approaches. So another example of the typical things we're doing in my team in crowd simulation is to escape this view, let's say, where agents are represented this way, like simple moving 2D circle on the floor, and where we consider that the interaction neighborhood are the few other agents nearby. And all this geometry and state of people will explain fully this trajectory. Actually, it's noticeable that real humans do not exactly behave this way, but they are more facing this kind of information, which is mainly visual, to steer their locomotion. And from this understanding of from this visual information, they are steering their locomotion. So we do replicate this. Let me go very fast into this because I think I have too much content here. But yeah, you can typically control the motion, and it's done in robotics with sensor-based control typically. That you can steer agents from what they see actually, and extract from those images some information that will help them, like performing target reaching kind of task or collision avoidance kind of task. Let me explain a bit that target reaching, for example, you will extract what is the position of objects in an image and try to get them in a specific place of the image. And or collision avoidance can be performed based on the optical flow you perceive in your environment, and how and the relation you have between the properties of this optical flow and the position of objects. I cannot go more in the details, but as you can see, we can steer this agent and go make it go through those pillars just by the image of what it sees and the sequence of those images and the resulting optical flow. Or you can do, for example, following by, for example, trying to cancel the optical flow generated by this red character. You will start moving with it. And you can so the process is this one. We establish the relations between self-motion and visual features that we can extract from images, and at running time we extract the visual features from image and we adjust self-motion according to these control laws that enables the character to perform local tasks. And you can do this and combine different local tasks and reach this higher level behavior, like for example here, navigating in the street based on collision avoidance and target reaching kind of flows, and we mix them in a simple way. This comes with sort of an energy function we try to minimize by moving. And interestingly, this captures more the relation we have between light and motion, or let's say the human visual motor loop, as we try to understand it. So I think here again, so it's all knowledge driven. I mean, we know what kind of feature we should extract from those images and the kind of control law that would enable those agents to perform successfully the task we have them. But there is this question whether this matches what humans do, right? And how we react to light, or how we control our self-motion based on the light we perceive through our eyes. So I think there is a way here again to try to predict things in following this kind of question, like what learning first the relations between the visual features of those sequence of images and motion, and then try to replicate them and predict what would happen in a new situation. And we are really like, again, I won't go in the details, but we are dealing with this kind of situation where also part of the information is missing because there is a lack of light, so there are dark areas. And in contrast with what we would have done based on geometry, we can really have a prediction of what this lack of light will generate in the trajectory. Like, for example, here, the character is finally avoiding those dark areas because we penalize somehow this lack of information. But again, the question is whether real humans are doing this, yes or no. So with this, I think let me go into a final example of complex interaction we try to predict. Would be I'm not sure how much you can see of this, but this is a real footage of Oasis concerts in Manchester. And what happened here is that you have this wave, a shock wave going through the crowd, literally, and starting from the back of the audience and getting front up to the stage. And you can see the same thing under different angles. So it's all on YouTube. You can search for those keywords and crowd search Oasis concert, and you will find this. And we try to capture what is the effect of these physical interactions between people into our simulation, and try to predict what would happen if, like, let's say, someone pushes back, and we are in this situation of high-density crowds, and how this would result into a dangerous motion eventually for the crowd. So this prediction is of course very complex, and it deals with physical interactions between humans. And we try to capture the complexity of these interactions, physical interactions between people, into those simplistic particle-based models, because obvious complexity issues. And it's all about, from example of physical interactions between people, try to model, try to learn, and try to predict what would happen in similar conditions whenever it happens. So for this, we are running experiments where we concretely push people actually and see how this motion propagates and how people exchange forces between them. And goal is really to abstract this into a data-driven model and then to predict what would happen in an observed situation. So here, eventually, the goal would be from the state of the crowd and what happens to predict the risk of such a wave surge to happen and eventually prevent it before it happens. So here the prediction takes another meaning. So now that it's more clear what let's say how this work coming from motion prediction can help simulation, we can turn the question the other way and try to see what we can bring to HTP. And I have to say that data is key for both fields. I mean, all our models, the parameters of them, or the evaluation of the simulation we're running, they are based on data. And so is the modern prediction techniques as well. So I will go a bit into what we do to collect data. I'm checking the time. I think we started late, so I still have like about 10 minutes, if that's fine. So I will try to spend 5
that's fine.
And keep time for questions. I will go immediately to the point. So what we do to gather data easily. So this circular experiment I showed you is it takes us months to prepare, eventually years to reconstruct the data and to publish, analyze and publish. So that's a very long cycle, and we try to shorten the cycle. It's really almost an economical problem we are facing here. So let me show you immediately. So yeah, what we do is we use virtual reality to collect data because it makes simpler and faster this process. So here I won't go into the detail, but we were interested into capturing both motion and gaze information to better understand who you are interacting with in the crowd, even though here the crowd is quite low density. And what happened is that we actually equip someone with this LHMP kind of VR equipment, and we make him walking through the virtual replication of real environments. We is populated in the same way, and we observe what is happening, and we can collect this data very quickly. I mean, at the end of the experiment, everything is fine in terms of data processing. There is no more step. And you have a full annotation of this environment because it's simulated. So you know what is what in all this environment. So there are many benefits, of course, at the cost of making sure that the behaviors you observe in virtual reality are the same than in reality. We can push this to extreme, so I won't go into this. So capturing full body motion data in dense crowds. But the extreme of this is what we call the one-man crowd paradigm. So, and we replicated this circle experiment I showed you in VR. So on the right, you can see the VR replication of the experiment. It's quite similar visually, even though there are little things here happening. I will explain why. What is happening here? It's actually not 28, because we have 28 people here, moving in a VR environment. It's only one. And one embodying and successively moving each of these characters. So it's asynchronous crowd data recording here. How does it work? So we have a video to illustrate. So on the top, you can see what is the real environment. So someone walking in sort of a gymnasium here. I guess the quality is not that good on your side. I'm sorry about that. Those videos are on YouTube. You can find them with the keyword one-man crowd. It's a paper this year at VR. And what you can see here is that this participant is going back to its initial position, or the one of these 25 characters here, and successively moving it and seeing the motion that has been recorded before. So to be clear, he moves character 1 and then embody character 2 and see character 1 moving as it did, and follow it, and successively like this, embodying all the 25 characters. So again, the question here is whether whether what you observed has any connection to reality. So these are movies, but okay, you have understood that actually this replication of the circle experiments was done by the same participant embodying each of those 28 characters. And you can see how a real motion that has been recorded here with 28 different people in real compares to this one recorded with only one participant and performing successively this task of following himself, actually. So I hope it gives perspective on this problem of data acquisition, which is the same for machine learning and for us, is that those trajectories, those motion data are extremely interesting for us, but difficult to acquire, or at least expensive. So we try here to cut on the cost of acquisition. That will conclude my talk. So and a few words to conclude. So how crowd simulation has perceived the growth of HTP, the field of HTP in robotics, typically a way to overcome all the limitations we have using knowledge-driven modeling. To be clear, uncraft model to say how agents should move one relatively to the other. And eventually also opening the way to perform automatic modeling. So given an environment and the recording of what is happening here, can we come with an understanding and some models of all the interactions that are happening here, or all the behaviors we can observe here at different levels? There are plenty of fascinating questions doing this, or like starting from the basic one, we are not sure that humans actually follow interaction laws as we claim in our models. There are questions about scale coupling. I went through them rapidly. What are the data set requirements to predict behavior? So all these usual questions you have in this field are actually, we have the same, and collaborating on this would be super interesting. And how to build a hierarchy of bare neural levels. I'm not sure I've seen some HTTP approach taking at the same time all these different levels from high level to low level behaviors, trying to explain and predict what would happen at long term in the details of the trajectories, but also all over the environment. Data is key. So using rich data set is important. And I think I've trying to push some ideas we have to have those data sets with plenty of annotations and information embedded. And I talked about the economical aspects of those acquisitions. It's not my work only. It's plenty of people here and plenty of projects that were funded by agencies. So I would like to thank them all here. And just to say that we are in the process of building this new team that is called Virtus, that will be located at INRIA. Thank you very much for your attention. And maybe hopefully I can take questions.
Thank you very much for your presentation. This was truly fascinating material. Thank you so much. I hope that the next speaker will forgive us if we leave the time for one or two questions. Luigi, do you see someone in the audience?
At the moment, not yet. So we do have a question, actually.
Okay.
Yes, please. Thank you.
Hi, thank you for the presentation. It was very insightful. So my question is that I can understand that doing microscopic high-density simulation of crowds would have applications in graphics and rendering in movies and games. but what could be the everyday, daily life applications? Why would we want to predict motion of such massive crowds? How could that be useful?
Okay, I will ask to if someone closer to the
Yes.
mic can repeat the question. I understand that it was about high density and daily situation.
Yeah, essentially the question was how can we, so in our daily life, so those macro simulation of crowds, how can we use it, right? Of course, many people in the graphics domain are interested in that, but can you give other examples, right?
Yeah, sure. I didn't mention this at the beginning. It's true that typically crowd simulation has two main applications. One is graphics, so and typically video games, visual effects in movies, etc. The other one is architecture and management of crowded events. To be clear, and we are dealing here with comfort issues, but also safety issues, and predict what would happen. For example, so I've shown on purpose that we were trying to address the relations between light and motion in our models, and typically to predict what would be the difference in evacuation time if you are experimenting a power cut, for example, that would shut the light in your environment. So you are about to evacuate, let's say, a stadium, but unfortunately at the same time, and maybe this is a reason to evacuate, you have a power cut. So and predicting all this, so today is done by asking people to gather in a place and do the experiment twice, one with the open, with the light open, and the one with light closed, right? Really, it's like this. Ship evacuation the same. For example, to see what is the effect of the angle of the ramp to evacuate a ship, they are doing those experiments where they install a ramp, they change the angle and see what is the effect on the flow. So if we have high enough quality in the prediction of this, all the effect of these different factors could be actually anticipated, could be predicted, instead of constantly trying. So the application of those are huge. And also another example would be to understand what happened in a given event, right? The Duisburg, for example, love parade events were re-simulated to understand, but what happened here, right? Was it a management problem? What is a behavioral problem? So, and what can we do to prevent this? So these are typical daily applications.
Right. Thank you so much.
We still have one question from the room, if this is fine.
Yeah, let's hear it, of course.
Yeah. Coming.
Hi, thank you for great presentation. I have one question regarding the crowd simulation. So in other examples, you have only the agents, people who are interacting with more or less static environment. How far away are we from the moment that actually the crowd simulator will be able to handle effects of cars and other moving objects, not only people?
Yes, this is a very important question for the car industry, for example, and I'm aware of existing work on what we would call multimodal interactions. So it's not only pedestrian, but also pedestrian cars and so. And also we addressed this with this crowdbot project I mentioned, because depending on the robot behavior, shape, or whatever action of the robot, predicting how people will react to this is a big question, because you will lack example here, especially when you are designing a new robot. And so I think again, data is the key, and we need to quickly learn interactions from first the few examples you dispose of this. So question is, for example, whether a pedestrian collision avoidance model would apply when a car is involved as well. So typically, do you avoid a car or another person? my understanding is, my guess is no, because the risk is not the same. So, and this will also impact the way you prioritize interactions. Like if you are facing, let's say, a bike, a car, a truck, and another pedestrian with unavoidable collisions, I would run to the other pedestrian eventually to escape the others. So predicting all this is really difficult. And I think the one quick question again is to be able to characterize better the application domain of the different models we're using, or the one we embed in simulation, to make sure that when we predict interactions with new objects or new vehicles, we are right or wrong.
Thanks.
Welcome.